Hi everybody. So in today's video, we're going to be learning Unit 2, Lesson 7, which is about estimating and interpreting derivatives. So our two learning targets for today are going to be I can estimate the derivative of a function using a table of values, and I can interpret the meaning of a derivative in context. So what does it mean in that particular scenario? Now, it's important to realize that today we're going to be learning about estimating. So before we estimate a derivative, let's review the rules that we know that help us find derivatives exactly. In this unit, we have learned that a derivative is the slope of a tangent line, it is the slope of a function at one point, and it is also the instantaneous rate of change. All three of those things are synonymous with derivative. So there are four different ways to say the same thing. Now, we've also learned some rules that will help us find derivatives. And when we use these rules, we are finding the value of the exact value of the derivative. So we are not estimating here. We're actually calculating an exact value. The first rule that we learned was the power rule, which says drop it, which means multiply. So we would get 8x to the, and then we would subtract 1, which means negative 1/3 power. We learned several trigonometric rules. We learned exponential rules. And what I did here is I put the actual function and the derivatives here for you so that you guys could see how those all lined up to review. We've got our product rule, which says copy the first, take the derivative of the second, plus copy the second, take the derivative of the first. And we've got our quotient rule, which we said is low d high minus high d low, and low squared goes down below. And we've got our chain rule, which says take the derivative of the outside, leave the inside alone, and then multiply and take the derivative of the inside. Now, the next thing we're going to be practicing is estimating the value of the derivative. We're going to need to use this method when we do not have an actual function to differentiate, because that would give us an exact value. But sometimes we don't have a function, we don't have an equation. We can still estimate what's happening at a moment in time if we have a table of values. So, when we estimate the value of a derivative, we're using the given information to find the best approximation of the instantaneous rate of change. We are often asked to do this when we're given a table of values. You'll notice I'm using the word estimate, approximate, because these are not going to be exact values. They're going to be values that are as close as we can get with the information that we have. An example would be use the table to estimate f prime of 1. Now you'll notice that in this table, we've got x, we've got f of x, there is no row for f prime, but we also know that f prime means the slope when x is 1. So in this table, the first thing I would do is I would try to figure out where would the 1 be. In this table, the 1 would be in between the 0 and the 2. So what we're going to do is we're going to find the slope between the two closest ordered pairs to that value, which in this case would be the ordered pairs 0, 0 and 2, 4. Now, in order to do this, you're going to do regular old-fashioned slope. So slope, the f prime of 1 would be approximately the change in y, in this case f of x, over the change in x, which would be 4 minus 0 divided by 2 minus 0, which would give me 4 over 2, which would give me 2. So my estimate is that the derivative would be approximately 2. Now, similarly, we can do this in a context. So sometimes we're given like time and height of a tree, years and meters, in which case, when we do this problem, we're going to want to label our answer with units because the problem has units in it. Again, this is the x value that we're trying to find the derivative at, and h prime means find the slope. Now in this table, the 1.5 would go in between the 1 and the 2. So we're going to find the slope between these 2 points, which are the closest we can get to 1.5. So I'm going to call it my h prime of 1.5 would be 4 minus 2, the change in the y, over 2 minus 1, the change in the x, which is 2 over 1. Now my units here would be meters on the top because the change in y goes on the top, per year on the bottom because the change in x goes on the bottom. Now that brings me to our second learning target of today, which is that these are estimates for, and I should make this an estimation, not an equal to, I apologize. These are estimates for slopes, but the second thing we're often asked to do is interpret the meaning of the derivative in the context of a question. Now, when we say the word interpret, that means tell me what it means in this scenario, like in this application. And to do that, there are 3 components you need to make sure to include. Every interpretation needs to have a noun, which means describing what you actually calculated, a units, so what units would be useful in that question to measure that item, and a time. So at what time or over what time interval did you perform those calculations? Now, we usually abbreviate that NUT, N-U-T, to remind ourselves that every interpretation should be N-U-T, or noun units time. So here's how we would interpret a derivative. When we're interpreting a derivative, we should always use the word rate of change as part of our noun. For example, you might say the rate of change of the temperature. So the word rate of change should be in there, and then what actually are you measuring? In this case, maybe the temperature. Now the units are always going to be a fraction. You need to divide the given units that are there. And the reason you need to divide is that a rate of change is a slope, which is change in y over change in x. An example might be degrees Celsius per hour, or meters per second, or feet per year. And you can write these out with the word per, or you can actually write them as a fraction. And lastly, time. So all derivatives are found at a specific time. So you would have to say whatever specific x value or input value you're using to find that derivative. So is it the rate of change of the temperature in degrees Celsius per hour at 1 o'clock in the afternoon, or is it at noon? And that changes how you do the problem. Note that if a derivative is positive, then the stuff that you're measuring is going to be increasing in quantity or value. And the stuff that if the derivative is negative, the stuff that you're measuring is going to be decreasing. So because a derivative is your rate of change, if a derivative is positive, the stuff is going up. And if the derivative is negative, the stuff is going down. Okay, let's go ahead and do number 1. It says a pan of brownies is removed from the oven and left to cool. The temperature of the brownies is given by the differentiable function t of x. Selected values of t of x are given in the table below. Estimate t prime of 7, show the work that leads to your answer, and then using correct units, interpret the meaning of your answer in the context of the problem. So let's start with estimate t prime of 7. There are really 3 kind of parts to this question. Let's start with estimate t prime of 7. To estimate t prime of 7, I'm going to start by figuring out where the 7 would fall in this table. In this case, the 7 would fall between 6 and 8. So I'm going to find the slope between these 2 points in order to calculate that derivative or estimate that derivative. So I would say t prime of 7 would be approximately 150 minus 170 over 8 minus 6, which means I would get negative 20 over 2, which is negative 10. And because this problem has units, I'm going to make sure to put units on my answer, so it would be degrees Celsius per minute. So that's part 1. Estimate t prime of 7. Part 2 is show the work that leads to your answer, which I did when I did part 1. And last but not least, using correct units. So it's reminding you that you need to talk about the units in your answer, interpret the meaning of your answer in the context of the question. So let's start with our noun. What are we finding here? Because we're finding a derivative, we are finding the rate of change of the temperature. So T prime of 7 is the rate of change of the temperature and then we need units. So measured in degrees Celsius per minute. And then we need a time at T equals 7 minutes. So we need a noun, we need units, and we need a time. Then we need to decide, does this mean that the temperature is increasing or the temperature is decreasing? Since our value here was -10, we would say since T prime of 7 is negative, the temperature is decreasing at that time. So noun, units, time, and does it tell you that we're increasing or decreasing? Because that's what a derivative does, is tell me if it's going up or going down. How is it changing? All right, that's it, folks. Thank you guys so much for watching, and I will see you in class for some practice problems.